Hello. The title of the talk is It Ain't Over Till It's Over. Well, if you are too curious about this title and try to search it online, maybe you only find a song that was popular like 3 decades ago. Now, this talk is about harmonic analysis, maybe not on music, but on Boolean functions. So let's first review some basic notion in the analysis of Boolean functions. So given the Boolean valued function f, we define the individual influence of the variable xi as the probability that you flip the value of a function by flipping the ith variable on a uniformly random input. The max influence is just the max individual influence. To help us internalize these notions, we look at two examples. Later you will see that these examples are relevant for the result to discuss. The first example is the majority function, which simply outputs the majority bit of its input. The max influence of the majority function is in the order of 1 over square root of n. The calculation is simple, so let's do it. For any variable to be sensitive, it has to be the case that it equals to the majority bit, and also in the input the number of zeros and number of ones differ by at most 1. Here is this example 0, 1, 0, 1, 0, 1, 0, and any 0 is sensitive. Now on the random input, the probability that there are almost the same number of zeros and ones is about 1 over square root of n. And conditioned on this event, any variable has a probability at least half to be the majority bit. So that gives us the bound 1 over square root of n in total, which is the max influence of the majority function. Now the second example is the Travis function. This is just the n function composed with the OR function, such that the fanning to the AND gate is said to be n over log n, and the fanning to the OR function or gate is said to be log n minus log n. And these parameters are chosen just to make sure that the function actually outputs 0 and 1 with approximately same probability on the uniformly random input. And the Travis function has max influences log n over n. This is also very easy to verify, so let's do it. So first I just say it suffices to check the case when the Travis function outputs 0. And it's easy to calculate that with constant probability there will be exactly one OR gate that evaluates to 0, and all the other OR gate evaluates to be 1 on the random input. So now any input bit to this special OR gate will be sensitive. If you flip it, you flip the value of the Travis function. And since the number of inputs to this special OR gate is about log n, therefore the max influence is about log n 1 over n. And that's just the probability that your input being sensitive, meaning your input being the input to this OR gate. So now for both these two examples, the max influence is very small, actually polynomially small, and the variance is constant, meaning that on the uniformly random inputs, it outputs 0 and 1 with about equal probability. And our focus will be such functions. If this is the first time that you encounter such function, you may find it a little bit weird. But these functions actually arise very naturally in many different contexts. The first one is the social choice theory. For example, maybe you and your friends want to decide how to spend your weekends. Some may prefer playing some indoor games, and some may prefer enjoying soccer on the grass. And to reach a consensus, you may just agree on the majority preferences. And you can, of course, define much more complicated way to aggregate social choice. For example, the way to elect the president in the US is maybe a majority composed with majority function. However, quite often the feature of such aggregation function is that no individual should be able to determine the outcome regardless of other people's opinion. And this is kind of captured by that max influence is small. For computer scientists, maybe the more compelling motivation comes from the study of the hardness of approximation. An important task is the so-called dictatorship test, where you want to distinguish the dictator function and the functions with small max influence. Here, dictator function means that a single variable can decide the outcome of your function. Well, a third reason to study these functions is that they actually have very nice properties. For example, they satisfy the so-called invariance principle. Roughly speaking, when no individual variable can decide the outcome of a function, then you can actually replace these Boolean valued random variables with Gaussian random variables. A very familiar example is the central limit theorem. When you sum a large number of Boolean valued random variables, it's like summing a large number of Gaussian random variables. So in the end, you get a Gaussian. Now our result is about what happens when you apply random restrictions on functions with small influences. To be concrete, maybe let's just say that a random restriction will restrict exactly Pn random bits by assigning uniformly random 0 or 1 to the fixed variable. Now I can actually say what's our result. So we show that you can apply random restriction to any balanced Boolean function such that if you restrict 1 minus 1 over about log 1 over the max influence fraction of the inputs, then the restricted function will be non-constant with high probability. So recall that the majority function or the tribes function, they have polynomial small max influence. So for those kind of function, you can actually restrict to up to 1 minus 1 over log n fraction of the input bits. And still, the restricted function will remain non-constant with high probability. So note that this is actually optimal just because the tribes function is a depth 2 AC0 circuit. Therefore, you can apply Haas-Switch lemma, which says that for depth 2 AC0 circuits, when you restrict 1 minus 1 over log n inputs, fraction of inputs, then you get a constant function with high probability. So also we can make this non-constant more quantitative. In particular, we can show that the restricted function will have large variance with high probability. Well, the actual behavior doesn't matter, it's not very important. But the actual behavior matches what happens to the majority function. Okay, maybe more remarks about this result. So this kind of problem was first asked by Friedgut and Clay in the context of social choice, and they pinned this name it and over till it's over. And a suboptimal version of this result was proved by Mosso, Donnell, Oleskiewicz. And furthermore, Kohler, Lifshitz, Minzer, Mosso, they have a different approach to obtain the optimal result. Now let's apply our result and show the following simple application. So we prove that for any balanced function f, on almost all inputs, its block sensitivity is going to be at least about log 1 over the max influence. Recall that the sensitivity of an input for the function f is just the number of sensitive bits, and the block sensitivity is the max number of disjoint blocks of variables that you can flip to flip the value of function. Now remark for this application first, we expect no such result for the sensitivity. This is just witnessed by the majority function. And second, by the famous KKL inequality, you can actually show that the average block sensitivity is at least log 1 over the max influences. So our result says that not just the average of block sensitivity is large, but in fact every input has large block sensitivity. Now let me sketch the proof. So just to fix a random input x and partition the variables into random blocks. Maybe take m blocks for some suitable m. Now note that when we fix a block, then the remaining blocks together with input x induces a random restriction. And when the restricted function with respect to this random restriction is non-constant, it just means that within this fixed block, there is a sensitive block. Now we can apply this to all blocks, and you can show that with high probability, a constant fraction of this block contains a sensitive block within themselves. So that's it. Now in the remaining of the talk, I want to discuss a little bit of how our proof works. Recall that what we want to show is we want to study when we apply random restriction to functions with small influences, what happens. Okay, so our approach is actually to study some random process and associate that random process with random restriction. So in the remaining of the talk, maybe let's re-encode the input of the function by -1 and 1 instead of 0, 1. So this is just re-encoding, nothing happens. And also, because we know that any Boolean value function has like the representation from the Fourier expansion or multilinear extension, we can view this function taking any real valued vectors into reals. Okay, so now let's start from the simple random process, the uniform process. In this uniform process, what happens is we're going to have a random permutation. This random permutation corresponds to a random order that we're going to use to expose our variables. At time 0, so in the beginning, no variables has been exposed. We're going to use the 0 vector to indicate that. And for time from 1 to n, we are going to expose a variable based on this random permutation. And when we expose the variable, we just fix it to be a value -1 or 1 with uniformly random probability. For example, at time 0, we have the 0 vector. And maybe at time 1, we expose the 6 variables. and maybe it's fixed to be 1. And at time 2, maybe we fix the third variable, and maybe it's fixed to be -1, and so on. Now we make a few observations about the uniform process. First, at time t, xt actually induces a random restriction that restrict exactly t variables. And also, in the end, at time n, we actually got a uniformly random element from the Boolean cube. Now if we feed a point at time t, xt, into our function f, the value actually has a meaning. It's just the average of the restricted function. And because a function f has a multilinear extension, so it's also very easy to show that fx0, fx1, etc. till fxn actually form a martingale. And finally, I want to mention that the influence of your function f for the variable I is just the average partial derivative of your function f evaluated at time n with respect to the variable I. Okay, so next I want to modify the uniformed process and get what we call conditioned process. The meaning of the name will be clear in a minute. So in particular, this process is essentially the same as a uniform process, except that when we expose a variable, we don't set its value to be a uniform uniform plus minus 1. Instead, we set it to be 1 with the probability half plus the partial derivative of a function at time t minus 1 with respect to the variable to expose divided by twice the value of the function at time t minus 1. And the actual formula maybe doesn't matter. It just comes from the fact that we want to sample uniform random element from the preimage of your function f. And this is very easy to calculate, so you can verify it on your own. And another simple fact that I want to mention about the conditional process is that if we fix some path, by path I mean maybe at time 0 we get the 0 vector, at time 1 maybe we expose the 6th variable, and maybe at time 2 we expose the 2nd variable, and so on. So that's a path. The probability that the conditional process follows this path divided by the probability that the uniform process follows this path actually only depends on the endpoint and the initial point. In particular, equals to the value of the function at the endpoint divided by f0. Recall that when we evaluate the function at time t, it actually corresponds to this meaning that is the average of your restricted function. And when the average is large, it means that within this subcube, there are more preimage of 1 for the function. Therefore, we expect that the conditional process will get to this path with higher probability. So the proof is also very straightforward. You can verify it. Now we will change our perspective. We will think a controlled perspective of the with the conditional process. In particular, let's consider the following game. So we are going to expose the variable in a random order. That's the same. But when we expose a variable, what happens is that with probability 1 minus epsilon, The variable will be set to -1 plus 1 with uniform probability. On the other hand, with the remaining probability, a player, maybe you, get to decide how to assign the value to the variable. The player's goal is just to sample a preimage of 1 uniformly at random for the function f. Well, if you think about it a bit, you'll realize that this is very hard for the player to accomplish if in the end she does not have the control. But this is not an issue for us actually, because we can actually just set a time n that is close enough to the end time n, and we say that after this time m, we just give full control to the player. And we can show that there is a strategy for the player to accomplish this goal, namely to sample a uniformly random preimage of 1 for the function f. Okay, so maybe why is this related to our result? Well, just know that the variables not controlled by the player actually determines a random restriction. And furthermore, note that if the player can sample uniformly random preimage of 1, she can also sample uniformly random preimage of 0 by using the same analysis. For example, now replace the function f by 1 minus f. So these facts combined implies that the restricted function is actually non-constant. Okay, so now let's just see how the player should play to accomplish this goal, to sample uniformly random preimage of 1. Now consider some arbitrary time t. We know that with high probability, the value of this variable to expose is going to be set with uniformly random probability. And also, when the player gets to control, what the player will do is the following natural thing. She is going to set the probability distribution so that the total effects is going to be the same as the conditional process. And if you decided to do this, then you can actually compute the probability distribution for the player. And it's going to be a half plus the partial derivative of a function at time t minus 1 with respect to the variable to expose, this divided by 2 times epsilon times the value of function at time t minus 1. The only issue is that for the player to implement this strategy, it has to be the case that this actually corresponds to a valid probability distribution. So epsilon times the value of a function at time t minus 1 needs to be larger, greater than the partial derivative of your function at time t minus 1. So let's just call tau the stopping time that this condition no longer holds for this random process. Well, for the purpose of our analysis, we are actually going to define the stopping time to be the first time when either the partial derivative become too large or the value of our function become too small. And our goal will be accomplished if we can show that the stopping time is going to be larger than m with high probability. Recall that m is just the time where we give the full control to the player. So once the player gets full control, she can do everything. She can definitely simulate the conditional process. Okay, so so our technical parts centers around the analysis on the stopping time that will involve the max influence, which kind of controls how fast these random process can perturbate. Okay, so that's all. Thank you.